Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. It's my great pleasure to introduce Professor Ramani Duraiswamy and Adam O'Donovan to give a talk on audio cameras for audio-visual scene analysis. Professor Ramani Duraiswamy is an associate professor in the Department of Computer Science and the Institute for Advanced Computer Studies at the University of Maryland, College Park. He obtained his Bachelor of Technology degree from IIT Bombay and a PhD from Johns Hopkins University. He currently directs research at the Perceptual Interface and Reality Laboratory at the University of Maryland. His current research interests can broadly include areas in audio for virtual reality, human-computer interaction, and scientific computing. Such as multi-core GPU stuff, and the computational machine learning and vision. So Adam O'Donovan is a PhD candidate and graduate research assistant at Department of Computer Science at the University of Maryland. He has BS degree in physics and computer science from Maryland. He received the NVIDIA Fellowship for 2008 and 2009, and University of Maryland Prime Fellowship in 2007 to 2008. He has been interned in a couple of places, including Microsoft Research. That was last year? Yes. So without further ado, let's welcome Professor.
Thank you, Cha. So I'm going to talk about some recent work we've been doing and a device we developed which we call the audio camera. And so our goal, the goal of our research, I guess it's a bit loud, so I'll move it down. The goal of our research is essentially doing scene understanding, and as well as sort of capturing scenes and reproducing them for remote listening, either sort of contemporaneously or sort of for later listening. And of course, if you want to understand scenes and sort of, it's quite often much more advantageous to use both the visual information and the auditory information, because audio and vision often provide sort of complementary information. And it's because sound travels relatively slowly, and it's able to capture lots of information in its time-varying signal. On the other hand, light is sort of very good for geometric and information because it's sort of pinpoint and so on. But on the other hand, sound sort of does not suffer as much from occlusion as light. So there's lots of information in both. And often, if you use both modalities, you get more bang for your buck. So the kind of information people want to capture out of sound is, of course, speech and sort of non-speech utterances. And there is sort of a tremendous amount of work which has gone on in speech recognition, automatic speech recognition, and so on. But most of that is sort of with close talking speech, so speech captured by microphones right next to you. But there's other information in sound. So for example, where the source comes from, and this includes both the direction and the range of the source, and the sound information which you receive in a room or outdoors often also captures information about the ambience. It has information about the reverberant structure, the materials of the room, the size of the room, and so on. All that information is available in the sound which you receive. And if you have the knowledge and location of the ambience of the source location and of the room ambience that can also help you in sort of extracting the information, sort of improving speech processing if you have sort of distant collection. Okay? So sort of a broad theme of our research is combining microphone arrays and cameras. And what we like to think is that in our approach to doing especially the audio processing part of our work, we differ from many previous authors in the sense that especially as far as the audio is concerned, when audio and video processing are done together, usually they're done separately. And integrations sort of happen between audio and video after the processing modality sort of, you've completed your job in both modalities, then you sort of fuse results. So especially in this work, what we try to do is we try to treat the audio also as a geometry sensor and thus as a camera, and try to treat audio and video in a joint analysis framework. So this is sort of lots of tall claims made initially. So let's sort of see what we want to do here. So as I mentioned, one of our sort of interest is source localization. And when we do source localization via audio, you want to use microphone arrays. And there are many approaches to doing source localization using microphone arrays. And the oldest techniques are based on solving sort of geometrical nonlinear estimation problems. So essentially, you know time delays of arrivals, for example, between sources, between microphones, and you try to solve for the source location by solving some nonlinear estimation problem. But this approach, especially in the presence of noise and reverberations, is known to be inaccurate. And another way which people have used in the literature is by doing sort of looking at what's called steered response power. So the idea is you use your microphone array, and you hypothesize that there's a source at some given location. You steer your microphone to point at a particular location. And if your hypothesis is correct, you get some gain in the signal received. And then you sort of repeat this test and sort of look procedure for many, many different locations. And if you then so choose, you can sort of display this image, this sequence of beams steered as an image, and you end up with an intensity image of sound arriving from particular points in space. And of course, this approach is interesting because it's sort of less prone to noise and potentially more accurate. And moreover, you can incorporate a priori constraints. So the disadvantage is your costs rise as the number of look locations increase, because essentially you have to sum up all the microphone signals, multiply them by certain weights, and potentially if you're doing a frequency dependent algorithm, you have to do it separately for each frequency, and this gets extremely expensive. So this is, I'm still sort of staying in an introductory phase. Now what I'm going to do is we're going to follow this approach. We're going to do beamforming, and we're going to sort of point beams at many, many directions, but we're going to use a special microphone setup, and this is the spherical microphone array. So the spherical microphone array is an interesting object. Essentially what we have is you have a spherical solid surface, and this spherical solid surface, you can sort of imagine on its surface there are a bunch of microphones, or in an ideal case you have a sort of a pressure sensitive surface. And it turns out that for this surface you can use the principle of acoustic reciprocity and you can very easily construct beam patterns for any arbitrary look direction. So suppose you have a plane wave arriving from a particular direction, say theta k and phi k. You can solve the equation for sort of sound scattering of the surface of the sphere, and you can get a solution for the scattered sound field, which is sort of given here. And this gives you essentially for a given plane wave what the sound received at any point on the surface of the sphere would be. So that would be the sound which would be recorded by a microphone, which would be placed flush on the surface of the array. And in acoustics, there's this wonderful principle. It's also there in light, which is called Helmholtz reciprocity. Just knowing this solution, you can also automatically find what the beamformer weights would be to sort of to do beamforming in this direction, theta k and phi k. So essentially, you can find the weights of by which you need to multiply the recorded signals to get back the response in a particular direction, psi theta k phi k. So the nice thing about this structure is that the beamformer weights can be sort of factored in a way that you can get essentially a beam pattern which looks like spherical harmonics. So what are spherical harmonics? So spherical harmonics are just like sort of they are Fourier series on the surface of a sphere. So in 2 dimensions, just like regular Fourier series are sort of a basis on the circle, spherical harmonics are sort of doubly periodic functions which form a basis on the surface of the sphere. And essentially any square integrable function on the surface of a sphere can be expanded in a series in terms of spherical harmonics. These harmonics look so you have one frequency parameter for Fourier series. For spherical harmonics, you have 2 frequency parameters. So in one direction, sort of you increase the frequency in this way. So essentially, this is north-south along the latitude. And in the second, as you sort of increase the second index, you have along the azimuth the order of the series increasing. Okay? And any function can be expanded in terms of spherical harmonics, and you can get so because now the spherical array, you know the weights corresponding to get a spherical harmonic beam pattern in a particular direction, you can now essentially compute automatically the beam pattern for any particular shape you would like for the beam. And this is sort of a gratuitous plug for our book, which I throw in a couple of times in every talk, so that to push the sales up, if any. Okay. So now let's sort of step back and see how you do spherical array beamforming. So suppose you want to find the beam response of this array in some particular direction theta, and you've sort of recorded signals now at S microphones, which are spread on the surface of the sphere. You compute these weights and you sum up and you get the response in that particular direction. And these weights themselves in general are sort of an infinite set of they involve an infinite summation, but since you will not have any, so that would correspond to the case where you actually had an infinity of microphones on the surface of the sphere as opposed to a finite set S. So instead you have to sort of truncate this sum at some number n minus 1, which is related to this number of microphones S you have. And so that is related to the number of microphones you have, and this order n minus 1. So the number of coefficients you end up with is sort of proportional to the number of microphones you have. So suppose you had 64 microphones, you could sort of end up you would truncate here at so that's 0 through 7. So you have 8. So you have 64 coefficients. So we did some sort of improvements to the original work of Elko, which sort of and Myers, which created the spherical array. And Elko, and so this is related to some technical issues involving quadrature on the surface of the sphere. Elko and Myers used particular designs for this spherical arrays, which required you to place the microphones at the locations of particular platonic solids on the surface of the sphere. And this was related to how you could sort of perform quadrature on the surface of the sphere. So the microphones had to be at the locations where you could perform quadrature on the sphere. But it turned out that their locations of the microphones, if even 1 or 2 microphones fail, you have problems and you can't do beamforming with these arrays. A previous PhD student of mine, Ziyun Lee, developed sort of general uniform layouts on the surface of the microphone array. He's also at Microsoft. I should have realized but he's in the live in your group, I guess. I should have called him. But anyway, he developed this theory of quadrature on the surface of the sphere, and using some previous work by Lord Thomson, where he sort of was trying to develop a theory of electrons on the surface of a sphere and had them all repelling each other. And it turns out that if you use these as your locations of the microphones, you get robustness with respect to quadrature error. And so then a few years ago, then Ziyun built this sphere where he essentially took a lampshade and he put a bunch of microphones at the locations corresponding to what this quadrature problem gave him. And we then proceeded to use this array for different things. And here are some pictures of his, which show that if these 4 microphones are missing, he still gets good quadrature error.
So the property of this arrangement is that it minimizes error or something?
Yeah. So essentially, this arrangement. So the thing is, what happens is this summation corresponds to an integral over the surface of the sphere, and these weights. So the location of these theta s, if you remember from sort of your numerical methods thing, usually when you do quadrature over some interval, if you choose your locations of your quadrature nodes, so for example, people choose Chebyshev nodes along the line and they get a better thing. So just like you have some special nodes, these nodes are selected to sort of minimize quadrature error.
Those are like bases.
Yeah. So they're sort of somehow optimally far from each other in some sense. Okay. So then we proceeded to build different arrays, and so these are actual experimental beam patterns obtained with these arrays. So this is an order 5 beam pattern. So this is a main lobe, and this is we built also a hemispherical array. So this was for a video conferencing application. So where we placed the hemisphere on a table, and you get the sphere is completed by the image of the hemisphere on the surface of in the surface of the table. So you get, for free, you get double the number of microphones because of the image principle. And with the same number of microphones, you're able to get much higher order beam patterns. So this is an 8th order beam pattern, which is relatively tight.
Yes, so roughly speaking, if you have a fixed number of
Microphones.
Placing them in the optimal configuration
Right.
versus from the line,
Right.
how much gain do you get?
Oh, so ballpark. Okay. So if you have 64 microphones, you can sort of get an 8th order beam pattern. So you can get sort of an n-fold square root of number of microphones improvement in the gain of the microphone array using the sphere. Okay. So, and we also use them to sort of track traffic as they went along, sort of point it along and sort of take it along and so on. But now we sort of get to the subject of the talk. What we wanted to do with this microphone array was to use it for audio imaging. So, which is sort of returned to the first theme which I mentioned. So suppose we use this microphone array, and this is a source in a room, say someone speaking. And we essentially digitally steer the beam at many angles and at many azimuths. So essentially at this direction, at this direction, at this direction, and so on, and make a map of the energy which is received. You do, so this is a Mercator projection. So this is like the sort of Earth's map which is put out. So essentially the top one spot is spread out. So just like Antarctica and the Arctic are spread out in the real world, you have a spread out location. So this is this person, but you can also see all his reverberations in that room as he's speaking because of the structure of this image. So now our goal is to use the spherical microphone array and create a device which can create this kind of image continuously at frame rates, and then use it to reason about the structure of audio scenes. Okay.
Quick question.
Yeah.
So what we see besides the main image,
Yeah.
those kind of light blue spots, what is this? Those are the side lobes, or those are actual reflections?
Those are actual reflections. There will be some side lobe contamination also, but the side lobes are relatively weak in this array. So there is some. So that is like a point spread function of a camera. There will be some spreading, but most of these actually you can reason, and you can figure out that these are actually the reflections.
So we can say that the lower part is reflection from the floor, we can
the upper ceiling,
and those are from the walls.
Right.
Wow.
And so we essentially transform the spherical array into a camera for sound. Okay.
So what kind of processing do you have to do?
I will come in 1 second. So what is the processing? Essentially, I will sort of, this is too many words. So essentially, we have a ray from the center of the camera in the look direction, and we have that energy there. And that is somehow spread by the beam pattern and side lobes also, but mainly it is sort of from that particular direction, and we create the image. Okay. So then we came with an interesting observation that this image is what's called a central projection image. So to those of you who've taken a computer vision course, you know this is sort of the first thing you learn about when you learn about imaging models, that the image model which is used for cameras is that it's a central projection camera image. So all rays of light pass through this camera center, which is the image center. And this forms the basis for the geometric analysis of images, and you essentially can use the tools of projective geometry to analyze images. Okay? So now the images which we are producing with this audio camera also have this central projection property, essentially all the rays are going through the center of the sphere, which is the imaging sphere. And because of this, we can essentially, we have the epipolar geometry. So suppose now I image a scene using both an audio camera, so which is this guy here, and a video camera. Then there is an epipolar geometry between the audio camera and the video camera. So essentially, suppose this person P is being viewed by the video camera. You can, and let's say P happens to be a face detector, which is run on the video camera. So now, when I look at the audio camera image, that person can't be absolutely anywhere, but in fact, they have to lie somewhere along this line in the audio camera space. Okay? And you can use such constraints between 2 cameras, between 3 cameras, and so on, and you can borrow this from vision. And moreover, now if I have 2 cameras, and I know the correspondence at 7 or 8 points in the world, then I can compute what's called a fundamental matrix between these 2 cameras, and which then allows us for any new points to find the epipolar line corresponding to this in the other image. So of course, when you have cameras, you do calibration. So we built a calibration target. So this is a pencil which has a tiny speaker and a tiny light source at the end of it. And we simultaneously image it using the audio and video camera. This is supposed to be an animation, so somehow the GIF is not animating, but anyway. And then you can sort of get the epipolar lines, so which is sort of shown here between the 2 cameras. And so here is the epipolar line from the sound camera sort of displayed in the audio image, in the video image, and you can see it's sort of passing through the light source.
So it has a light source
and a sound source, which are co-located. So now we want to create these images in real time, right? So we need to do some processing to create these images in real time. So the nice thing is, of course, this beamforming is digital. The weights are known explicitly for each direction. I don't have to, I can sort of just use the formula. Each direction, the beamforming is independent. And there is some sort of, with some math, you can either do it using time domain signals or frequency domain signals, depending upon your application. But this is sort of relatively expensive. That requires this sort of each pixel. So in light, we are very lucky. Each pixel essentially gets almost for free the image from a particular ray. But this is like if you had a camera and you had to sort of sum up all the pixels' outputs to get what is for a particular direction. This is what's happening with the sound camera. So now we have an expensive computation. And yeah.
Furthermore, do you have to do it for each frequency?
We can do it for each frequency, but there's also a time domain formulation we can do which can save up something. I didn't go into that, but there is a way to do it in time domain. But usually we do it frequency by frequency because the frequency representation gives us more interesting ways of doing things. I'll come to that in a second. So we need to somehow speed this up and get it running at frame rate to produce video images. So of course we can use parallelism, and it turns out that the first setup which sort of people did with this trying to do this beamforming, they were doing too many extra computations which were not necessary, and we could use some special function tricks to reduce the number of computations. So it turns out that there was an inner sum which involved sum of spherical harmonics. And this inner sum, it turns out, we can use what's called the spherical harmonic addition theorem and reduce this sort of n special function evaluations, actually 2n special function evaluations and this sort of summation into just one evaluation of the Legendre polynomial for one angle cosine of gamma. And these cosine gamma, so this essentially corresponds to the angle between the microphone location and the look direction. So if we have a table of look directions, we can just sort of store these angles corresponding to sort of specific look directions in a table, and we don't need to, in fact, do this special function evaluation all the time. Y and M are these spherical harmonic functions which I sort of showed a few slides ago. So it reduces M multiply and adds to just one cosine evaluation. And it turns out that there was another sort of complicated function, and which is here, this guy here. And it turns out that if you sort of go back to look at sort of ordinary differential equation theory, which one learns, there is an expression called the Wronskian, and so which takes sort of functions which are sort of Bessel functions which correspond to J and H, and their products are just a simple, it turns out is a simple polynomial, and that again that function evaluation can be also simplified, and of course then we can use parallel processing. So now we've reduced the cost of each direction, and we are going to use the fact they're in parallel, and we are going to, and in fact it's trivially parallel to get really fast beamforming in each direction. And if you speak of parallel, you go to sort of graphics processors, and these graphics processors, so this is actually now a little bit dated. This is a couple of years old. This is the NVIDIA 8800 GTX, and actually this is the one we used. But if you use the later NVIDIA, it's the speed is somewhere here. It's at a teraflop now, and you can. We are able to run this thing at 100 frames a second with still some computation to spare. Of course, Dell didn't used to sell these computers when we wanted them, so we had to buy computers which had funky lights in them from these game manufacturers. Yeah.
So that's 100 frames per second of what kind of resolution?
Yeah. So the resolution is relatively coarse. This is related to so the resolution was about 10,000 pixels to get 4 pi coverage of the room.
Doesn't it also depend on the number of frequencies you're?
We were doing it at about 20 frequency bands, which were covering, and I glossed over some details. So for example, the lower frequency bands, you cannot do very high order beamforming. You can only do order 2 and order 3 in 100 hertz and so on. But as you get to the kilohertz range, you can do higher order beamforming, which gives you sort of more resolution images. And those images which I showed you were corresponding to the 4 kilohertz band. So that's an important distinction which I jumped over. Okay. So now I'm going to show you some images of this sort of real-time thing. So this is the image of how the calibration was done. So he's essentially taking, and so he's sending off the sound and at different locations. So once that's done, you can do some interesting things. So once you have the calibration done, the next thing you can do is you can do image transfer. So now with Yoni in the hall, I'm sort of scared to talk about image transfer, but anyway, I'll still talk about image transfer. So suppose I have 2 cameras, and I assume that the world is far away, right? So then just knowing the fundamental matrix, I can do image transfer between 2 cameras. So and so I'm going to show you. This is the. So here, Adam is going to switch on a speaker. So the top is the audio image, and we know the fundamental matrix between these two cameras. So we're going to transfer the audio image to the video image. So we switch it on, and as soon as he switches it on, those pixels light up, which is where the sound is coming from. And so now he'll sort of go through, he's speaking, he's flicking his thing, and so on, and you can sort of find, and you can get an idea of the resolution. So that pixel in the regular image essentially comes much, much bigger.
The false colors?
The false colors are actually that we are showing RGB images. R, G, and B are different frequency bands which are mapped to the sound color.
So the bot there is what?
Is that spot in this resolution?
I see.
That resolution is very low. As I said, whole 10,000 pixels is basically giving us 4 pi. And this is just a very small sort of field of view, and you're looking at this.
We'll have them snap, then
Yeah.
it's move down there, and
Yeah.
then when you talk, you
Yeah.
move back to your mic.
Yeah.
That's pretty slow.
No, it's
We're using a little bit of filtering so that the image persists for a little bit, so that it doesn't sort of immediately disappear after you snap.
A speaker.
yeah. So now let me show you some more applications. So the next application, so here we can sort of consider that this application was essentially audio is helping video to find out where the sound is coming from. So now let's look for an application where video is helping audio. Yeah.
I missed something. From this, you would only have an axis over that's coming from. The camera and the audio camera are not collocated, so
Right.
you should have like a ray.
So this is the point I was making, that if you assume that the world is far away and it's on the surface, both the objects are far away, then if you know the two cameras and you assume that the source is, you can get the direction and you can project onto this direction. To do it exactly correctly, like you're saying, with the range information, we would need 3 cameras. Then we can do sort of image transfer between 3 cameras. But this assumption actually works.
So in this case, the camera and the audio camera are reasonably close.
They're reasonably close, yeah. And so now I'm going back to the same one. Okay. Okay. So now, in this application, what we are doing is we have Adam, and we have the video camera and the audio camera, and there's a very loud sound source. Okay, and this sound source is music. It's playing very loudly, and we are going to try to beamform, use the epipolar constraint to help beamforming. And in this, I'm going to play some sound. So essentially, the first is sort of the sound without beamforming, and you cannot make out what Adam is saying. And then you'll just hear the sound, which was obtained by searching along the epipolar line for the peak. And in this case, you'll sort of be able to make out what he's saying. And there was no sort of tricks like Ivan uses of post-filtering and all this wonderful stuff used. If you use those, that would be even better. Pure beamforming.
So your music is really 1, 2, 3, 4, 5.
Now with beamforming along the epipolar line.
8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25.
The microphone, that huge thing,
That's the spherical
so
microphone.
it's big.
No. The one in the back is actually something else totally.
Oh.
It has to do with head-related. This is the microphone.
Oh, okay.
That little white thing. No, we have that also is a microphone array, but that measures your head-related transfer function if you step in. But that's in the lab.
So how far is the music source from Adam?
So both are relatively the same distance to the microphone array. Okay. So you can also do sort of things with multiple sources. So for example, we did a lot of experiments with sort of two sources, how identifiable they are. So that those are all reported in a paper which is in the Transactions of Audio Processing. It's in press, how close they can be, and you can still identify how far apart and so on. Okay, yeah.
In that case, you're just doing the beamforming in the direction you estimated. You're not trying to steer nose or anything.
No, nothing. So this is very trivial beamforming, which is sort of just the main lobe. Okay, so the next idea was, in audio, most people know that if you have a room, you get reflections from all the walls in the room, and that affects listening quality. Especially in concert hall acoustics, people are very interested in designing the concert hall so that you have good direct path. There are some early arriving reflections which have to be distinct, and late arriving reverberations have to be sort of attenuated, and so on. And this is indeed a sort of a black art which architectural acousticians do. So could we use the audio camera somehow to help architectural acousticians? And so we went and measured. Essentially, this is a very nice music hall which is at the campus of the University of Maryland, and this is a panoramic image of this place. And here we placed a sound source on the stage, and this is a spherical panorama which is sort of unwrapped here, and you can see this hall. So now I'm going to play you a demo of a slow motion movie which we got. So I'm going to now display the spherical panorama in this fashion. And so now this is on a sphere, so it sort of looks more reasonable, and the sound source is located here. Okay, so as I play this sound, you can see the sound come off. It's a very short chirp, and then you can see the sound reflect off the walls. You can see the location of the reflections. You can see it's reflected off the floor, of the back wall, and you can sort of, this is a short 10 millisecond chirp, but as you sort of keep going along, you see for several seconds, essentially all the reflections in slow motion, as sort of you can see, it's now reached the ceiling. You can see the reflection of sound, all the locations. Oh, by the way, this these colors are sort of normalized so that in each frame, the maximum color is the same, is red. So the maximum intensity is red. Otherwise, they would be attenuating, and you would see sort of damped out colors. Okay. So essentially, we've shown this to several architectural acousticians, and they're very, very excited because apparently it takes them 2 months to fix a hall after it's built. And having such tools, they can sort of go and they get these things. Of course, we need a much more portable audio camera to do that, and we are sort of working on that. I'll show that, as I'll show in a second. Okay. So
after many seconds, it's still very coherent.
Right. It is, and it's amazing.
I would have expected the full room to eventually be filled with.
Yeah, it is. If I keep going, I sort of stopped it. But if I sort of take it along, as time goes on, you'll sort of see it's not. So there are so many reflections all over the place, as sort of at later times that.
So the whole time sequence is a second here.
It's second. It's more. It's sort of it goes. The screen is not there. It goes to about 2 something seconds. So, but the original chirp was only several milliseconds, 10 to 12 milliseconds, something like that.
One single shot.
Chirp. Yeah, that's it.
And so we're seeing this is repeat in a loop or something.
No, it's still going on. It's
Several hundred milliseconds since the.
Where's I see.
Slow motion. So 700. So that's 700 milliseconds. And this graph on top is then like the.
So what?
Yeah, it's cut off a little bit. That's sort of a plot of what the maximum value in that particular image is as a function of time.
So that's how you see that.
You see the decay.
So how can you see which one is the secondary, first the reflection and secondary reflection?
Okay.
Well, it's actually difficult to identify exactly what order the reflection is.
Yeah.
in this case, but,
It's hard to identify, but now we're going to sort of come to another use. So the next goal is, of course, we did this for concert hall. So can we use it in room acoustics somehow? So in room acoustics, we all know sort of reverberation is often treated as something to be not a friend. It's bad. It sort of screws up our algorithms and so on. And though there have been people since the 80s and 90s who have sort of thought of doing what's called matched field processing. So the idea there is, suppose I know the source and I know the room impulse response, then I can potentially invert this room impulse response and clean up the sound field, right? But so the most famous person who sort of worked a lot on this area is Jim Flanagan, and he essentially wrote several papers trying to do this idea, and even one of his students is also at Microsoft, but he's moved to Live Labs also, or Search Labs, Arun Surendran, and they worked on this area of trying to do basically match field processing. But what they found is even a small error in the room impulse response essentially destroyed the results. Okay, so now the thought we had was, is there some way we can use this this audio camera with the visual camera to figure out which reflections are actually obtained at the microphone array, and can we use those in some interesting way to improve the signal quality as well as do dereverberation. So this is essentially what I just said. So what I'm going to do is now going to show you this movie. Well, that's not it. I guess it didn't launch. Yeah, no, it's here. Or maybe I'll just go to the directory. Where is that?
yeah, there it is. You can just execute reverb. We could probably not be executing it. Just the end code.
Oh. Okay. I'll have to. So it's sort of all. It's doing something.
Actually, probably it's lost the connection to the VPN. And it's hangs on some university.
Okay. So let's. I'll go. I'll show you the demo at the end when sort of MATLAB recovers. Let's. So what is our algorithm? So essentially, what we do is we go to a room. We record different people speaking. So that room in which we did this recording is about a third of this, or even maybe a fifth of this room size. It's a small conference room. And we had two sources speaking simultaneously. And our goal was to essentially find the reflections which corresponded to each source, use the spherical array, and point the beam for the direct at the location of interest, and also find those reverberant reflections which are visible to the array and which correspond to the source of interest, and clean up the sound while suppressing the other sound and simultaneously dereverberating. Okay. So the first thing we needed was a mechanism to figure out which reflections correspond to source A and which reflections correspond to the distracting source. And to do this, we need to sort of build a similarity function which essentially looks at the beamform signal coming from the source of interest and all reflections and see if these come from the same source or they come from a different source. So we used MFCC features to do that. So here is sort of images from the audio camera. This is with the images corresponding to one source, the images corresponding to the second source, and the images corresponding to when both sources are present. And on the left, we are showing the MFCC similarity metric, which is computed on the beamformer output. Okay, and the right two panels correspond to that similarity metric applied to the image when we have both sources present. So essentially, when we had both sources present, the image should have looked something like this, but we are able to suppress these other reflections and only have those reflections which correspond to the female alone. And similarly, for the male, we are able to suppress the female reverberations and get those reverberations which correspond to the male guy.
How to interpret the second one? It's one
Okay.
single source.
So this image is the audio camera image. This is for the male alone. For the female alone, for the male alone, and this is for both of them.
So those are the lighter
Reflections.
that the reflection.
Reflection. And here, this is now we run this MFCC similarity guy for every direction, and it tells us this location, this location, this location, and this location, and this location are the locations of the reflections for the female. And we run, so this was run first on the case where we had the female alone, and now we ran it also on the case where we had both the female and male speakers, and we are still able to sort of locate the reflections which correspond to the female. And likewise, we did it for the male alone and for the male in the presence of the female, and again we are able to locate the reflections which correspond to the male speaker. So now, since we know, so the idea of the algorithm is we beamform to not only the source, but also to the locations of the peak of the similarity metric. And now we are going to do delay and some beamforming, but for the beamformed signals from the spherical image output.
So suppose rather than using spherical microphones, you're using the regular arrangement. How much worse is that going to be?
I don't know, but this is a very good question, and this is actually hot off the presses. This is work we did last month, so I'm just and we also during the course of this research we also developed a very good time delay estimator, and now we are sort of checking how good because it works very nicely in reverberant environment. For performing sort of delay and some beamforming, we need to figure out the delay between the reflected image sources. And so here is sort of the single channel source. This is the after the doing the approximate match filter, our process, and this is the original. And we get significant improvement, at least to perceptual quality, but we need to run some more tests to sort of give you quantitative, say, PESC scores or something like that to tell you how much improvement we've had. Okay. So now let's sort of look at the evolution of the hardware. So if we want to use this guy, and we want to sort of have many people use this guy, we need to give it out in a portable format and have it go around. So the first one we built, I said, is the spherical array, and you can see the amount of wires coming out from each of the microphones sort of here. And of course the hemispherical array was nice because we had all the hole in the table. We could sort of take this huge braid of wires and take it there. But this makes the whole thing very unportable. So we want to get it portable. So about 2007, 2008, we tried to develop a portable version. And this is a 32-channel array, which we developed. And we moved all the analog to digital conversion electronics into the center of the ball. And so this guy just has one power and one USB wire coming out of it. And there is some FPGA stuff going on there, which essentially takes all the analog to digital and packs it into USB and sends it out.
32 channels
in one wire.
One wire. Okay.
And now we...
You said 2.5 megasamples per second.
Yeah.
And you use 16 bits.
This one is 12 bits. But we could do 2 point, but we are actually using very small percentage of the available bandwidth.
Yeah, that's the question.
So we can go to 256 if we wanted. Microphones at 24 bits, so now the version we developed earlier, end of last year, is now 64 channels. So this is a 5.5-inch sphere. And it has one camera which is also built into it. So this is a single USB camera, and this is what. So this is the camera looking out. We can look out with this. And now we sort of we license the design to a company in our area, and these guys actually now building an array which has 6 cameras which sort of stitch panoramas at the same time as they are sort of taking the panoramic audio images. And so you can sort of, and it's much more rugged. These guys, they sort of build enclosures and so on. They are trying to ramp up and try to sell these things to. The radius is about 5.8 inches, which is about, yeah. They can do it smaller too, but this is the. So I sort of started a few minutes early. I'll just sort of finish by sort of saying some other applications of the spherical array which we are doing. One is we are also want to use it for remote reality reproduction. So we want to essentially capture reality at some point, say take you in a concert hall and then have the ability to place you in that concert hall. So we capture this, the spherical array sound. Then we do we convert the sound field into a plane wave representation. So we know the plane waves which are sort of impinging at that location. And now if I know your head-related transfer function, I can place you at that location by taking those plane waves and convolving them with your head-related transfer function. So that's, and then this is the scene recording, scene playback. So as far as head-related transfer functions are concerned, these are sort of things. So I'm just going to sort of skip very quickly to this thing. So it turns out that human beings, when we hear sound, we don't hear the actual source sound. The sound which is actually received at our ears. So if this is the envelope of the frequencies of the sound which was sort of from the source, the sound which is actually received at your ear is quite different because some frequencies are enhanced and some are attenuated because of the process of scattering of your own body. And so you are changing the color of the sound. Okay? So when you're changing the color in light, this would be like taking a CD and moving it in light. You'll get lots of colors in light because the wavelengths of light correspond to the sort of bumps on the surface of the CD, so you get these color shimmying. So just like that, when you move in sound, you are changing the color of the sound which is coming in your thing. And the interesting thing is that this process of changing the color of the sound, which is different for every person. So every person changes the color of the sound which is received differently, and this gives you sort of additional cues to do source localization. And if I want to reproduce virtual reality and I want to sort of give you very stable source locations in sort of audio presentation over headphones, I need to know this transfer function for every individual. And measuring this transfer function, and every individual's ear shapes are different, and so the transfer function is different for every person. And measuring this transfer function used to be a relatively tedious affair. What you would do is you'd sort of take a speaker, play a chirp from one location, then play a chirp from another location, and so on. And you would sort of do this over 2 hours and maybe 1,000 directions, and that would give you this head-related transfer function. But we used an idea which is often used in vision also, which is called Helmholtz reciprocity. And what this principle states is, suppose I have a sound source at a given location, let's say here, and I have a receiver here. If I swap the location of the source and the receiver, I will get the same measurement at the receiver location. So this is sort of showing you that in simulation. Even though the overall acoustic field will be totally different, between the 2 points there will be this principle of reciprocity. So we use this idea to measure head-related transfer function in few seconds. So the idea is we place headphone drivers turned out in people's ears. We use that microphone array which you saw in the background, and we record the received signal for all directions in one shot, as opposed to sort of doing direction by direction recording, and we can get this head-related transfer function. And if we compare the head-related transfer function measured the 2 ways, we get the same thing. So this is some related to sort of scene reproduction work. We also do sort of computation of head-related transfer function, computation of scattering. So now we are developing sort of arrays which are not necessarily spherical shape, but say head-shaped or other shapes. So suppose I put microphones on some arbitrary scattering object like a robot, a network of microphones. How can I beamform with those microphones? So then I would have to solve the wave equation to get those beamformer weights, and sort of we're working on those. But we're going sort of too many different directions, so I think I'll just take this opportunity and conclude, and thank you all for inviting me here.
One question
Yeah.
for you. When you
Yeah.
put your phone microphone inside the ear, speaker.
Yeah.
So if you beep,
It's too loud? No. It's we actually, what we did is we first seal the ear, okay? Yeah, and then put the speaker on some. But since this is a sort of important question, what we did is we also put a microphone. We took a dummy head, and we put a microphone inside the dummy head and the sealed apparatus, and we sort of checked what is the dB level of the sound. It was only 65 dB, which is much lower than any even sort of, it's like conversational speech level. So this was, otherwise, you know, it would be wonderful. You can measure everyone's head-related transfer function, but they're all deaf. But they're all deaf at the end of that procedure, which is.
That solves 2 problems.
Right.
So it's mainly matter of the HTRF. It's mainly matter of geometry of the ear.
Yes.
It also has something to do with the material.
Almost entirely geometry. Little bit on material.
So if you are able to measure geometry, then
It's stuck. You have to kill it.
Oh, it's still stuck.
Yeah.
So if you were able to just measure geometry of each person's ear,
You can do that. You can compute it.
right?
But its computations is relatively expensive still. So.
Okay.
Yeah. First you and then you. Okay.
So I'm wondering about the spherical array and how, I mean, it's like 64 microphones. What if I put like 8 by 8 on some planar array?
You can do the same kind of processing and create those same kind of images. The only thing is, especially with these weird geometries, if you put it near the wall, or if you have, so you have all these edge effects, and to sort of get reliable beam weights to get sort of the same gain in each direction and so on, it's harder to do with regular arrays. So for example, edge array, the edge microphones have different weights, those kinds of things. So there are constraints. But in principle, if you could compute easily the beam weights corresponding to each direction, you can use any procedure to create those images. So the spherical array buys you this sort of nice mathematical framework to get the beam.
I guess grad school learned about Fourier optics, right?
Yeah.
So it's like the far.
It's very similar to Fourier. Yeah.
Is the Fourier transform.
Right.
So it's easier to. I mean, it seems easy to think about the spacing between microphones as being, like if big spacing, then it's going to have a tighter beam.
That is correct. So, for example, if I have more microphones on my array, I can go to higher order, and I can get tighter beams. So, for example, when we went from the 64 microphones on a hemisphere, we got 128 microphones. So we could sort of get order 8 beams out of that setup. Whereas with the regular 64 microphone array, we could only get order 6 beams. So that's which are how tight they are. Okay, so this is the demo I was trying to show you, which sort of died. This is the Adam. Can you sort of pan around the room? So this is the room in which we did the experiment for. So what we did is the experiment had 2 speakers, and we played Timmit database frames.
Once I connected to the server, it sort of loaded every attempt we had previously.
Oh, it was all queued up. Okay, so here is the room. You can sort of, there's a table in the middle. So it has a very complex structure. So if you wanted to estimate the impulse response using simple geometry or so on, it would be very hard. So now play a sound source. So this is one. Yeah, so that's one speaker playing a sound source. You can sort of see it's reflecting of the table, of the wall, of the side wall. There's a second order reflection in that wall, of the whiteboard, and so on. There are all these reflections. So the goal is of that idea of somehow to use these reflections to do both dereverb and cleanup. The room is about this direction 24 feet, and width-wise it's about 11 feet. So this dimension is 11 feet, and this dimension along the table is about 24 feet.
This is also continuous sound.
So this is continuous sound because the sound is sort of pumping into the room. It's not a chirp. It's a continuous speech.
So how can we see it coming and going?
Yeah, so it's supposed to be just continuously.
It's continuous noise. So every once in a while, if you could see that plot, unfortunately at this resolution you can't see the plot. What we're showing in this particular image is just the high frequency, say 4,000 kilohertz band, or 4,000 hertz band. And so what you see in the energy is that when the energy happens to drop off because sort of randomly generated signal, that's when you start to see the reflections in the room. So unfortunately you can't see that plot at all. So what you'll see is you'll have sort of short bursts of say 5 or 10 milliseconds where the energy in the 4,000 hertz band is dropped off, and that's sort of these points where you see the reflections come through.
So of course, speech, when people speak, there is sort of interruptions and so on. But at the same time, it doesn't decay like in the other case because the person keeps repeating speech.
I guess I still don't quite understand. So if it's only 5 meters across, then it'll take 10 milliseconds or something to reach across the room, right? So if it's a continuous sound, why aren't we just seeing it like emit from the direct path and then see the...
Okay, you do see the direct path, so you can see the direct path go off and come on, go off and come on.
But this is not real time, right? This is
no. This is very slow, so it's only just 500 milliseconds.
Yeah, that's the time.
Right. Yeah.
Actually, so why do we see the direct path go off?
Because that speech segment got over.
Oh. Okay.
It's speech segment.
Okay.
It would be a little more clear if they hadn't chopped the graph on the top of the energy. But unfortunately, I guess when you try and use this program at a low resolution, it chops it. Fix that.
Because it's easier if you just show like a short chirp.
Right.
And the chirp will disappear.
Yeah, but the chirp gives you the impulse response. But it's sort of, but this was actually if you played a chirp, of course, you could use that to identify the impulse response.
That's right. Yeah.
You could do that. But so the goal here was not to do that. The goal was to say, suppose we just take this device, and we know nothing about the thing. We don't have the ability to play chirps. We don't have anything.
Oh, right.
How can we clean up the speech and record it?
Right.
So the reverberation time of that, I mean, we didn't get into the reverberation there?
Yeah.
It was about 200, 300 milliseconds.
300 milliseconds for that.
But because the signal was sort of continuous, you will always see something being imaged, whether it be actual direct rays or reverberations.
Okay, but it looked like, I mean, we didn't see a lot of color from other places, so.
Yeah, most of it was the direct energy. If you look at sort of the accumulation over a short period of time, that's when you get the image from the previous.
So you can sort of see the other side.
Where you get sort of the spots that correspond to actual reflections become persistent. If you sort of average these images over and keep a running average, then you can see where all the peak locations are actually
accumulating.
So, and that's what we use in
MFCC.
extraction.
But things aren't just sort of becoming ambient
No.
reverberation though, right?
Yeah,
No, it seems like.
that's right. I mean, presumably if we played, like say, like a quick impulse, we would see a decay into some level of ambience, but it would happen much quicker than, of course, in the conference hall.
Yeah, and at the same time, if you played some continuous noise in, then you may see all these sort of standing waves develop and so on. That also we didn't do here.
So I mean, this example, so you have to identify
Right.
for each response, for each observation,
Right.
you have to identify which source comes from by matching the MFCC features.
Right.
So if there are multiple people, it's going to be a.
Yeah, so we only tried so far with two sources. And we are able to distinguish the reflections of the two sources cleanly.
Because like you try the female and male,
Yeah.
probably the
This is the easiest, of course. And so of course there are many people who have sort of researched. So we would have to build stronger metrics, which are not based on just MFCC, maybe something else. But anyway, this is sort of well-studied field. We have to borrow their ideas, but this is just a first pass. Yeah.
So I have a question. You treat this microphone, right, as a camera.
Right.
I wonder, it looks like you're treating it as a pinball camera. I wonder, do you actually also have like focus or things like that?
So we are working on some concept which is the focal length, of course, is the sort of the radius of the array, which is the. But we are working. Your question is sort of interesting. For example, can we build a telephoto lens for this camera?
Right.
And we are working on some ideas like that, trying to see if we can. So that's work in progress. If it happens, we will. Sure. Yeah.
You mentioned that the company is going to build the product out of this. When do you expect this to be available?
So they are going to build 5 next month. The first 5 units will be built next month. And then they have sort of 2 or 3 potential customers. If they are able to sell to those, they will continue building. And otherwise.
It's not a mass production.
Yeah. Yeah.
So out of that device, are you going to get discrete channels, or will there be a lot of processing?
So the device is just going to send you in a USB, the two USBs. So one will have the image stream, which is the camera, and the other will have the sound, which is sort of packed channel by channel.
Okay, so in the computer then would be
the processing
into the image.
Right. Yeah.
Just to make sure I understand, when you're doing the spherical, you're just computing transfer function from that direction to that one, and then you essentially multiply that inversely and you delay the sum, essentially.
Right. So no, actually not transfer function. What we are doing is we are doing, so for example, because we have the image channel, so the way this would be used with the actual speaker is we would run a face detector. We'd know by the face detector what are the locations of the people.
Yes, suppose you actually know the source. So
yeah.
What do you do next?
So then once I know the primary direction of the source, I take the beamform sound from that direction.
But the question is, how do you get the beamform sound?
Using the spherical array and the knowledge of the source location.
Yes, I know, but what are you using from the source location? It's like the source location, I have the geometry of the thing.
Yeah.
So what did you...
So now I run my spherical array beamformer.
So what's the coefficients of the spherical array?
Those W weights.
Those W weights. With those.
What are they based on?
They are based on plane wave scattering of the spherical array from that particular direction.
So that essentially is equivalent to say, well, the particular microphone is going to have a gain and a phase.
Right.
And then you invert that and then add them up.
Right.
Okay.
Precisely. From that direction. I know the solution for that direction. And
calibration phase to trim the weights.
We don't need to calibrate too much. If you calibrate, so for example, there are some corrections we could apply. So these weights correspond to infinite, to far field weights. If you want, you can sort of correct those weights for near field weights. And there are procedures to do that, but we don't do that.
Oh, I see. You don't like to do that.
Yeah.
It's okay. I mean,
yeah. So if you're sort of within those weights, the corrections would have to happen for our sort of size array if you're closer than a meter to the array. If you're more than a meter away, you can still use the far field weights.
Correct the gain or just the phase?
Sorry?
You correct the gain or just the phase?
We would have to correct both the gain and the phase. But the correction, so there are, this question has been studied a lot in the literature for head-related transfer function because this is exactly the same thing again, which is studied, which is measured in that context, and it turns out that there are approximate geometric expression you can get how to correct the phase, how to correct the gain, both. But if you're beyond a meter, and our sphere is about head size. If you are beyond a meter, you don't need to correct those, or it's sort of less than so many dB, whatever that is.
Okay, let's thank speaker again.